Hi guys, we're going to take a look at binomial probabilities. Some of these problems appear in your probability packet. Binomial probabilities occur whenever the four conditions below are met. Number one, there have to be a finite number of trials. Number two, there have to be two possibilities on each trial, either success or failure. Number three, the probability of success on any single trial is the same, and we'll call that P. And number four, the trials are independent. So for example, what's the probability that exactly 2 5s show up on 3 rolls of a die? Well, let's think about this first. There's a finite number of trials because there's 3 rolls of a die. The probability of success is the same on any single trial. It's 1 out of 6. The trials are independent. And there are 2 possible outcomes, either success or failure on each trial. So in this problem, the first thing we're going to do is list all the mutually exclusive ways that this event can occur. We could get a 5, and a not 5, or 5, not 5, and 5, or not 5, 5, and 5. So those are all the ways that this can occur. The first one is probability 1 out of 6, 1 out of 6, 5 out of 6. Then the next one, 1 out of 6, 5 out of 6, 1 out of 6. And then 5 out of 6, 1 out of 6, 1 out of 6. You'll notice that these 3 probabilities are exactly the same. So what we could do is just write 3 times 1 6 times 1 6 times 5 6. But let's look at this in a different way. If we really want to count the number of ways to get exactly 2 5s out of 3 rolls, we would say the number of ways to do that is 3C2. Now, each of those ways has probability 1 6, 1 6, 5 6, which is 1 6 squared, 5 6 to the first. So the total probability would be 3C2 times 1 6 squared times 5 6 to the first. What if we looked at the problem where we wanted to know the probability of exactly 1 5? That would be 3C1, that's the number of ways to get exactly 1 5 out of 3, times 1 6 to the first, times 5 6 squared. 5 6 squared because there would be 2 non-5s. What about exactly 3 5s? That'd be 3C3, 1 6 cubed, 5 6 to the 0, because there'd be 3 5s and no non-5s. Let's look at another example. Suppose that 40% of the homes in the U.S. have recycling service. Find the probability that out of 10 randomly selected homes, exactly 3 have the recycling service. Binomial because they either have the recycling service or they don't. There's a finite number of trials. The probability of success is constant for each one. It's 0.4. And the trials, the houses that we randomly select, are independent of each other with regard to recycling service. We know from the previous problem that this probability is 10C3. It's the number of ways that we could have exactly 3 homes out of 10 have the service. And then the probability of each one of those events is 0.4 cubed times 0.6 to the 7th. Why? Because 3 of them have the service and 7 don't. And remember, with the 10C3, we're really counting every single way that you could have exactly 3 homes have the recycling service out of 10. Could be the first 3, last 3, middle 3, or any combination of 3s. We can do this by hand, or we can allow our calculator to do it for us. If we hit Math PRB, go to the binomial PDF key, we type in the number of trials, which in this case is 10, the probability of success on a single trial, which is 0.4, and the number of successes, which is 3. What if we had a problem like this? Find the probability that 4 or fewer people in the sample have recycling service. If we were to do that by hand, then literally we'd have to calculate every single probability starting at 0 going up to 4. In other words, there could be 0 people out of 10 that have the recycling service, or 1, or 2, or 3, or 4. Each of those is a binomial probability that we could calculate. We could do that by hand, but it'd be a lot easier to let the calculator do it. The calculator has a function called binomial CDF, not PDF. PDF is for one single probability calculation, right? CDF is for many. Now, the other thing to note about CDF is that probability goes from the lowest possible value, which is 0 successes, up to the maximum, which in this case is 4. The way they wrote this, it only goes from the lowest up to a number. Well, what if you wanted to find out the probability that there were 5 or more people in the sample who have a recycling service? I just said that the binomial CDF only goes from the lowest up to a number. But if you took 1 minus binomial CDF, that should be 10, 0.44, that would be 1 minus the probability that we had 0, 1, 2, 3, or 4 people who got the recycling service. And that's how we would solve that problem.